planar hexagonal structured layer of carbon atoms. Frequently you can meet information that this is a single atom material. If you look at experimental measurements, then you can see that the thickness of graphene, this is from experimental paper, is between 2 and 3 nanometers. Therefore, most probably this is not a single layer, single atom layer, but 2 or 3 stacked layers. But anyway, it is very thin. And this thickness is considerably smaller than the wavelengths, even in optical range. Therefore, as a result, in modeling, you can safely assume that graphene is zero thickness. However, it is conductive. The electrons go through these cells, but each cell dimension is also small, something like 10 nanometers. Therefore, again, this can be neglected in optical range and even more in terahertz and microwave range. What is very interesting, graphene is conductive, and this conductivity can be modified by using electrical or magnetic field biasing. Still further, it is transparent in optical range. Actually, what is shown here is a piece of dielectric substrate on which graphene is somehow deposited. You do not see graphene, you see only the substrate. And it is very strong. It is said that it is stronger than stainless steel, for example. So this is attractive material, first of all, because of the tunable conductivity. Today, one of the main areas of application of graphene is found in the bio and chemical sensoring. Here is a figure borrowed from a paper. It shows patterned graphene. There are graphene strips. Each of them can support so-called Plasmon resonances. I will explain further what it is. And the frequency or wavelengths of each resonance depends on the refractive index of the outer medium. Therefore, by measuring these resonance peaks, one can judge about the concentration of some material in the analyzed medium. And this is the physical basis of the sensing. These resonances are here in the infrared range. Therefore, the strip width, each strip has the width measured in nanometers. However, if you make the strip wider in micrometers, you can shift these resonances into terahertz range. And I will be concentrating on this topic. But in fact, the most interesting application in graphene is probably in future. You can feel as engineers that if you have something tunable, electrically tunable, then you can use this effect for building a modulator. And in fact, the center of gravity of studies around graphene is now near to the creation of efficient modulator in terahertz range. If this is realized, then a lot of new technologies, including communication technologies, will appear. Okay, so from the viewpoint of the modeling, as I said, a sheet of graphene can be considered as zero thickness. However, it is characterized by the conductivity, which is surface conductivity, or inverse value of this conductivity, which is surface impedance. This surface impedance of graphene sheet is complex. It has not only imaginary part, it has also real part, which corresponds to losses. Therefore, graphene is good conductor, but still lossy. And if we study if such a sheet can support electromagnetic wave propagation, we can use boundary conditions and arrive at the result shown here. A sheet of graphene in free space is able to support a surface wave with this propagation constant. This value is complex because that impedance is complex. Therefore, the wave will be decaying when propagating. But anyway, this is a surface wave which sticks to the sheet of graphene and whose field decays exponentially the normal direction to the sheet of graphene. And the origin of or physical basis of such a effect can be analyzed quite efficiently. The center of gravity, of course, is how to characterize the conductivity of graphene, how to reproduce the features of this surface conductivity. This cannot be done within the framework of Maxwell equations. Here you need to attract the quantum physics. But anyway, it has been done. And the most widely accepted model today is called Kubo Formalism. This formalism involves a lot of several of graphene parameters borrowed from quantum physics. For example, the Boltzmann constant, and also the Planck constant, and the Fermi-Dirac distribution function. And this value at T is the relaxation time of electrons, electron relaxation time. Anyway, these are the formulas for the conductivity. The total conductivity is the sum of these terms, but in the microwaves and terahertz wave range, the first term dominates. And you can see that the frequency is in the denominator. Therefore, the conductivity goes down with frequency, and impedance is going up with frequency. If you transform these formulas into plots, you can see that a sheet of graphene has the imaginary and real parts of the impedance depending on frequency as follows. Imaginary part goes up with frequency, and the real part, which is responsible for losses, is much smaller and more or less constant. Also important is the sign of the imaginary part of graphene. This sign corresponds to the so-called impedance or inductive behavior of the sheet of graphene. And this is the physical foundation of existence of such surface wave. You see, this surface wave has this constant of propagation along infinite sheet of graphene. But as soon as we pattern graphene or structure it, means cut out some finite sheet, finite piece of graphene, the same surface wave is able to bounce back and forth between the edges. And this creates standing wave resonances. Okay, so our goal was to develop a theory predicting accurately the electromagnetic behavior of a stack of strip gratings embedded into dielectric slab. We finally were able to have finite number of these gratings, but I will show the results related to only one grating like that. The electromagnetic scattering problem was formulated in a classical way involving Helmholtz equations for the scattered field plus a resistive type boundary condition involving this surface impedance on the strip surfaces, plus H condition which limits the field singularity at the sharp edges of the strips, and radiation condition at infinity. Further, we reduced each of these problems for each of polarizations to integral equations for the unknown strip current, current induced on the strip. And here there is a great difference between two polarizations. E-polarization corresponds to the electric field of the incident plane wave, which is parallel to the strip edges. And H polarizations corresponds to the electric field normal to the strip edges. In the E case, we reduce the problem to the integral equation of this kind, where the unknown function is V, this is the current, and the kernel function is the Hankel function, which is Green's functions for 2 dimensions. It has logarithmic singularity, so it is a weak singularity. However, in the H case, because of the different type of boundary conditions, we obtain the kernel of the integral equations, which has double differentiation of the Green's function. And this results in the hypersingular kernel. hypersingular kernel is very bad or ugly thing, because if you introduce a meshing of the domain of integration and make this mesh denser and denser, this does not correspond to better and better accuracy of reproducing the hypersingular kernel. Therefore, something more clever should be done. And what we did was the projection of these integral equations on the specially tailored polynomials. I will not go further into the mathematical details, but anyway, what is shown here, again, E wave and H wave case, logarithmic singularity split here analytically, and hypersingularity split here analytically. It happens that the integral equations with these kernels have a specific property. They possess the sets of functions which are orthogonal eigenfunctions of these singular kernels. In the E case, this is the first kind Chebyshev polynomials, and in the H case, which is more important and more physically interesting, this is Chebyshev polynomials of the second kind. So we make projection of the integral equations to these polynomials and use their property, being orthogonal eigenvalues. In this way, we reduce each integral equation to the infinite matrix equation with these chronicle deltas at the diagonal. This corresponds to what is called in mathematics Fredholm second kind operator equation. And this is very good because for these equations, there are so-called Fredholm alternatives or Fredholm theorems, which guarantee the numerical convergence. The larger is the number of truncation of this matrix equations, the better is accuracy. And in fact, to have practical accuracy of 4 or 5 digits, we need something like electric size. The number of the equations should be slightly larger than electric size of the strip, and that's all. This demonstrates the convergence of the results estimated by the norm in L2 by as a function of the number of equations. They oscillate but go down quite quickly. And now I will switch to the review of physical features of graphene grating. So at first I will be showing the results corresponding to the infinite grating of strips made of graphene and placed in free space. So only strips of graphene. By using this sophisticated mathematics and reliable tool of computing, we obtain such kind of frequency dependence of the reflectance, transmittance, and absorbance of the graphene strip grating, where each strip has a width of 20 micrometers and period is equal to 70 micrometers. You can see these spikes and dips. They correspond to the resonances. And what are these resonances? To answer this question, it is necessary to visualize the near field. Then we can see that in the first resonance, there is one bright spot of the field which is sticking to the strip. This is one period shown here. At the next resonance, we see 3 bright spots sticking to the strip, and further 5. So they correspond to the effect which I mentioned in the beginning. These resonances are created as standing waves because of surface wave excited on a sheet of graphene, but now bouncing between the edges of each strip. Because of the normal incidence, this is for normal incidence, the resonances on these standing waves with even number of hotspots cannot be excited because the symmetry of the incident field is orthogonal to those resonances. But if we incline the incident wave, then they will be also excited. So this is what happens in the normal incidence. And here is similar for, this is for oblique incidence or inclined incidence. You can see the same resonances. So each resonance is a dip in transmission and peak in reflection, but also peak in absorption. And you can see that the power absorbed in the graphene grating is more or less the same by magnitude as the power reflected by the grating. However, now at the oblique incidence, the number of resonances is larger. And this is because now the field, the odd index plasmon resonances can be excited. You can see two hotspots here, for example. The frequencies of these resonances in the first term, in the main term, are given by this formula. They depend only on the width of the strip and the surface impedance, but they do not depend on the period of the grating. Therefore, we can see that each strip resonates separately. The coupling between separate strips is negligible. Further, one can see that this coupling becomes more or less significant only if the strips are separated by the gaps measured in several nanometers. The quality factors of these resonances are not very high, but not very low, between 10 and 100 approximately. Okay, so this is the free space case. And finally, there is a comparison between two polarizations. The solid curves are for H polarization, they show resonances, and the dash dotted curve is for E polarization. It does not show any resonances because the plasmon resonances are polarization sensitive. And in fact, this kind of comparison shows us that a graphene strip grating can demonstrate what is called Hertz effect. A dense grating is well reflective for H polarization and well reflective for E polarization, but almost transparent for H polarization. However, now the range of the Hertz effect is shifted very far into the lower frequencies. It is not wider than the shoulder of the first plasmon resonance, which can be tuned. And therefore, the application of such effect is limited, but is tunable. But still, it is interesting to see what happens when the grating is embedded or deposited on a substrate, because in fact, it is difficult to arrange graphene, structural graphene, to be suspended in free space. Still possible, but difficult. More frequently, you meet such structures deposited or attached to a substrate. So now the same grating, but inside a finite width dielectric slab with certain permittivity and illuminated by the plane wave of E and H polarizations. Then the same numerical algorithm can be modified, and what we have as a result. We see, again, these curves are for transmittance, reflectance, and absorbance. The width of each strip is 15 microns, the period is 100 microns, and parameters of the substrate are 2.25, like Teflon, for example. And relative thickness is 0.5. So these are resonances. We can see that some of them are the same plasmon resonances as in free space, but now they are shifted. And this shift corresponds to square root of epsilon. Therefore, they are shifted because of the presence of the slab. But still, what is interesting, besides of those medium quality plasmon resonances, there are others. Some of them are very sharp, and the others are much lower in quality. They can be understood as different resonances of different classes, and they should be classified like that. Therefore, the letters P will be reserved for plasmon resonances, but these letters S and G will correspond to different resonances. One of them is called grating resonance or lattice resonance, and the other one corresponds to slab resonances. we will start with the Plasmon resonances. Here they are shown more explicitly. They are shifted to the lower frequencies because of the substrate, as I mentioned, but they are still well visible, and the visualization of the near field demonstrates us the same feature as before. 1, 3, and 5 bright spots sticking to the strip. What I mentioned in the beginning about the mid-infrared application in sensing was working on these first-order plasmon resonances of each strip. Now the formula is like that. It involves square root of epsilon in the denominator. The rest is the same. However, the other resonances are even more interesting. First of all, there are these super sharp resonances at certain frequencies. What are they? They correspond to the rule that the period of the grating is equal to the wavelengths of the guided wave of the bare dielectric slab without a grating. Therefore, they are well predictable, and they are caused simply by periodicity. The main term of the frequency is given here. It depends on the period. You can see that it does not depend on the width of the strip, for example. And the quality factors in theory for this infinite grating model can be extremely high, many orders of magnitude higher than the resonances of surface plasmon type. And finally, low quality resonances, these sinusoidal variations, sinusoidal peaks, they correspond to the slab resonances. They exist even without any grating. The visualization of the near field gives these patterns, and the frequency in the main term depends only on the thickness of the slab, and that's all. No strip width and no period. However, the quality factors are very low, between 1 and 10. So this is the main result of such a simulation. I can show more curves like that. And what even more interesting, we can easily plot the maps of the reflectance and absorbance as function of 2 parameters. You see, each section of this map with a horizontal line is a curve like that. But we combined several hundred of them here, computed with small step, to produce this beautiful figure. And there are ridges on this map, on this relief. Wide ridges correspond to slab resonances. This bright ridge corresponds to the plasmon resonance of the first order. But those super narrow ridges, they are zoomed here, correspond to the grating or lattice modes which appear because of periodicity. And actually those resonances are the most attractive in applications, including sensing, exactly because they have high quality factor. So this is all what I was going to say. Conclusions are summarized here. Graphene is very interesting material, but it can be characterized with surface impedance, and graphene can be modeled as a zero thickness sheet. So this is very convenient for modeling. Graphene can support TM-polarized surface waves, which can bounce back and forth between the edges of patterned graphene. And this is a physical reason of so-called plasmon resonances. Analysis of structures like shown here, like strip grating, should be done very accurately, and this can be done using the specially tailored projection schemes which guarantee the convergence of numerical solutions. What is interesting, such a tool which was developed here is approximately 3 orders of magnitude more efficient than well-known HFSS numerical code. With HFSS producing these maps or reliefs of functions, of of reflectance is absolutely out of question. It will take years of computer time. But with this sophisticated tool, it was possible to do that within a couple of hours, for example. There are many interesting physical effects related to graphene, including classical Hertz effect, but now shifted to lower frequencies, even lower frequencies than with metal gratings. And still, the most interesting effect is related to the appearance of the super high quality resonances in the case of a grating deposited on a substrate. This opens the way for thinking about new elements of terahertz range, new components and new circuits, and finally new applications and new systems. Thank you very much.
Presentation. Now we have time for one question. Who would like to make a question here, maybe? No? No? Okay. If it is not the case, so thank you very much again. It was great. Thank you. Okay, let's go now to the next presenter.